Do you see that? That is exactly what it looks like. Frost. Because even if this engine exhaust is hot enough to melt steel, the engine itself is freezing cold. This is only possible because this engine flows extremely cold propellants through the walls of the engine to protect it from all that heat. This is called regenerative cooling, and the fact that this engine does it with both propellants using an aerospike design that was 3D printed in copper is absolute insanity. But wait, because it gets better. Because this entire engine is just one part.
This video was brought to you by Aura.
The best part, as Elon Musk says, is no part. And, the next best thing is one part for everything. And it's a monolithic engine. So you have engines like the aerospike, which are made from one part. There is basically no assembly except plugging in the hoses.
This is Lean, a software engineer with many years of experience. And this is Josephine, an aerospace engineer that worked in Formula One on the car that Lewis Hamilton won one of his championships with. They met, fell in love, and created a company. As you do. The funny thing is, it's not a rocket company. The name of the company is Leap 71, and they developed an algorithm called Neuron. This algorithm is not just able to make rockets, but it can actually design anything.
Usually,
If I failed, I would get shocked. Eventually, I would learn what usually works, without ever knowing why. Neuron is different. Neuron doesn't learn by watching examples. It knows what the match is made of, how friction generates heat, how combustion works, and what physical conditions are required for ignition. From that knowledge, it can derive how a match must be struck, even if it has never seen one before.
Now, Neuron can't actually strike a match because it doesn't have hands. But what it can do is design full-functioning rocket engines. I know because I've seen it.
This is one of the engines that Neuron designed. And so is this, and this, and this. Did you notice what they all have in common? They all worked perfectly. But from all of these, this one is my favorite because it's pure insanity and the pinnacle of difficulty in rocket engines. And I want to try my best at explaining why.
Okay, imagine I want to build a rocket engine, which I do. What do I need?
Well, for starters, I need to choose a type of rocket. And rockets can either be liquid rocket engines that use liquid propellants, or solid rocket engines that use solid propellants. There's also hybrid rocket engines, but those are trash, so let's skip over them. Let's say we choose a liquid rocket engine, because we can actually throttle and shut those off.
Next, we need to choose the propellants.
Propellants is what we burn in the rocket, and one of them needs to have oxygen, because you need oxygen to burn stuff. So why not choose the best oxidizer possible? Liquid oxygen.
The only problem with using liquid oxygen as a propellant is that oxygen doesn't really like to be a liquid. In fact, you have to cool it down to minus 183 degrees Celsius just to make it a liquid. It's what is called a cryogenic propellant. As a fuel, we're using kerosene. It's easy to get, cheap, and loves to be a liquid. In fact, it insists on it.
The injector injects and mixes the propellant into the combustion chamber. They cannot mix before, otherwise you get an explosion. Let's go with an impinging injector, where you basically angle the propellants at each other so they smash violently and create small droplets you can burn.
Okay, now we have a way to inject the propellants, but we need somewhere to inject them into? What we need is a combustion chamber and a nozzle, so we can make the most out of those combustion gases.
We can either go with the dual valve nozzle, which is effective, easy to build, and it has been tested several times over many years. Or we can go with the wild aerospike, which is better at adapting to different pressures, but super hard to build and even harder to cool.
Yeah, I think the Laval design is the obvious choice. Did you notice how I said the aerospike design is harder to cool?
That's because our propellants, when lit up, burn at a temperature of over 3000 degrees Celsius, which is more than enough to melt any metal we can use to build our rocket. But we are in luck. We can just flow the kerosene through the walls of the engine to absorb some of that heat, and by warming it up, it's also easier to ignite.
Wait, the kerosene? Not the oxygen? But the oxygen is much colder. Wouldn't that make it the obvious choice for cooling? Well, yeah, but also, just like I said before, oxygen doesn't like to be a liquid.
You see, if the oxygen absorbs too much heat from the engine, it will boil off and turn into a gas before it reaches the injector. That same injector we designed for liquids and won't work with gases. Sure, liquid oxygen at minus 183 degrees Celsius would cool the engine much faster, but kerosene doesn't boil as easily. Don't get me wrong though, using kerosene is still super hard. Just to give you an idea of how hard it is, the F1 engine from the Saturn V that took the man to the moon used kerosene to cool itself off. To achieve that, they used many miles of thin copper tubes that were braced together to create the channels that cool the combustion chamber and the nozzle. If any of those brace joints failed, 1969 would be remembered for another reason.
Yeah, but this is 2025. We can't just 3D print the entire thing.
Through the process of using a laser that melts metal powder, line by line, layer by layer, you can get a metal part that has extremely complex geometry.
To use both, especially on the smaller aerospikes.
I mean, just the oxygen part is super tough. I mean, if you don't do your cleaning right, now your engine just self-ignites. I mean, just by running the oxygen through it, you have a little bit of oil left somewhere in your channels, the engine will just ignite.
Leap 71 started by designing small engines that use liquid oxygen and kerosene. They use different materials for the engines, like aluminium, which melts at 660 degrees Celsius. On the other side of the spectrum, they tried Inconel, which is this special alloy that can withstand up to 1400 degrees Celsius. They also tried copper, because copper is great at conducting heat. They tested different levels of thrust, different injectors, and different engine designs. All of this was so they could get the data from the tests and feed it to Neuron to make it smarter.
Smarter is not the right word. It makes it more experienced, because that's the way Neuron works. It evolves in a very organic way. It takes the data from the tests and uses it to improve the following designs.
Before they tested the 20 kN Aerospike Insanity engine, they tested an equivalent 20 kN Delaval design that used just the liquid methane to cool the engine. This engine was actually printed in two parts, and it used special and very expensive Teflon seals to keep the propellants from leaking. One thing that I found interesting was the shape of the combustion chamber of the Delaval design. It looks like a bottle of port.
By expanding it slightly, we're slowing down the propellant as it travels through the nozzle, and we increase the residence time, which should increase the likelihood of combustion, so it increases the combustion efficiency.
Neuron is not perfect. As you can see, the exhaust of the Insanity engine is burning green, and you get green flames when you burn copper. The engine didn't get destroyed, but they had to shorten the test because of a small part of the spike that wasn't getting cooled enough. And because of that, it was literally turning into fuel for the engine. That's what you call an engine-rich combustion.
But that's not even a problem, because they're not trying to design the best rocket engine ever, they're trying to create an algorithm that designs the best rocket engine ever. That's the point. Now they can just feed the data to Neuron, and the next Insanity Aerospike engine is gonna be perfect. Or near perfect. A big thanks to Lynn and Josephine for letting me record their tests, and also for letting me ask a bunch of dumb questions. I mean, thanks to them now I have more knowledge that I can use to build my own liquid rocket engine. I don't have Neuron, so I'm gonna have to figure something out. Thank you so much for watching, and remember, tomatoes are disgusting.